Hi there. In this video, I want to talk about this paper, Spatially-Adaptive Filter Units for Deep Neural Networks. If you have seen the WaveNet paper that I have explained, this paper can be really helpful for improving that, and also it brings a new concept. And this is published in 15 March 2018. The main idea and concept is very simple. It says that when we have a convolutional neural network, the number of parameters are defined based on the number of filters and number of kernels that we have. So if we have a kernel like this, 3 by 3, so we know that we have a limited, or maybe let's say fixed receptive field. And after some layers, so we have some max pooling in here. And those kind of max pooling is just increasing the receptive field, but we are losing the resolution. So there is a trade-off between the size of the receptive field and resolution. This paper says that instead of defining a fixed kernel and having different weights here, and these are our weights predicted by the neural network, maybe we can define a Gaussian function here. So instead of having a fixed size, maybe I can define a Gaussian function that has the average and also the standard deviation. And based on that, it could be in 2 dimensions. So we have mu1, mu2, and maybe sigma1 and sigma2 for images. And for signals also, it can be just 1 dimension. And these mu and sigma can be set by the neural network. So we just define how many kernels do we have. And for each kernel, we will define mu and sigma. So this is high-level overview of this paper. There are some implementation for TensorFlow, which is written in C++. We try to write it in Torch for the first time. The first sentence in the abstract, it says, classical deep convolution network increase receptive field size by either gradual resolution reduction or application of handcrafted dilated convolution to prevent increase in number of parameters. So you remember that we had the dilated convolution in WaveNet. So in each layer, we have a different dilation factors. And that's one of the way that we could have a bigger receptive field when we want to process signal. And here, it's also mentioning we can have gradual resolution reduction, as I explained here, that we have different layers. And after that, we have a max pooling that do the resolution reduction for us. And in this paper, we propose a novel displaced aggregation unit. It's called DAU, that does not require handcrafting. In contrast to classical filters with units or pixels placed on fixed regular grid, the displacement of the DAUs are learned, which enable filter to spatially adapt their receptive field to a given problem, as I explained here. So instead of a fixed kernel, we have a Gaussian filter. So they also mentioned the classical network apply small filters and implicitly increase the receptive field size by gradually reducing resolution via pooling layers and increased steps, as I explained again here. But in dense prediction problem, like in segmentation, sufficient resolution is required for accurate localization of segmentation boundaries. Thus, large receptive fields have to explicitly be accounted for without resolution loss. So in like unit architecture, if you look at those architecture, we have lots of convolution layers, and we are decreasing the resolution. After that, we have the decoder that try to retrieve that high resolution segmentation. But by using this, they are claiming that the accuracy can even increase a little. The most important thing is that the number of parameters can reduce a lot, and also the resolution can maintain. Instead of having like 9 different parameters for 3 by 3 filter, we will only have like 4 parameters for a Gaussian kernel. So another thing that they mention is this point that large dilation significantly violate Nyquist theorem, resulting in grading artifacts. So we didn't care about the Nyquist theorem when we implemented the WaveNet paper, but that is also interesting. I didn't know about that. And also the dilation factor or another hyperparameter that is manually tuned. So you remember that in the WaveNet, we try different dilation to find a good solution. But in this work, we don't care about the parameters. Maybe we can set the sigma, but the mu can be detected by parameter, or we can have both of them as a parameter, and system can learn them. So the mentioning here, the main formulation of a convolutional neural network can be defined like this, which X is the input and Y is the output, and F is the activation layer. But for DAU, Displaced Aggregation Unit, we suppose that this F, this activation, is convolved with a Gaussian function, as I show it here. And that Gaussian can have a displacement because the mu is like a displacement. If you have an image in 2D, the mu is the place that we put the kernel at that point. So that can be decomposed to this. So this is very simple. The main idea is very simple, but seems very interesting. And they also show that they could gain very similar result to when we use ConvNet, but with lots of less parameters. And this is some of the example, like for each layer, they have DAU, and they showed the DAU. These points are the initial point, and after convergence, it could find like this average and that standard deviation. Yeah, that's it. I don't have any other points about this paper. If you have any, please put it in the comments. There are different results on different data set to show that the DAU is effective. And as I said, there is no implementation in Torch, and we want to implement it for the first time. Hope it can be used for many other application and research.
So I have implemented the code in Visual Studio Code, and I didn't have any GPU. That's why I thought that it's good to have it in the Google Colab. So I will share it in my GitHub and the link in the description. But let's jump to the code. And also, I don't want to put time on writing the code together. So I have prepared it somehow that we can go to each line and see what's happening in there. And it's still running. I'm running it on GPU, and because on the CPU, I couldn't reach to less than 2 loss, which means about 30% accuracy on CFAR10. So the paper mentioned that the accuracy they've gotten on the CFAR10 is about 54, 57. That is achievable, but needs about 100 iteration. I just tried now based on 100 iteration. Maybe we can get that, I hope. And let's jump to the code. So first we need to see that what CODA do we have, what GPU do we have? We have Tesla K18, the Colab free version. And then we need to import some of the library, and I'm setting my device to the CODA. So I have created a DAU module in Torch. And what we need here is define an input channel, how many input channel we have, how many output channel we have, and how many DAU unit we have in each DAU class. So it means that, for example, we have 3 DAU unit. It means that we have 3 different Gaussian in one 2-dimensional space. Based on the paper said that they set the sigma to 0.5. You can see from the paper. Let me open that paper to DAU unit. ConvNet. Yeah, so you can see that the code that they have is in the TensorFlow, and mainly it is written in C++. I haven't used that code. I changed the concept of writing that a little. So this is the main paper, Spatially-Adaptive Filter. So let's see some of the parameters I'm talking about, like sigma is equal to 0.5, and we can define max kernel size, which is the size of the image. CFAR10 is 32 by 32. So the kernel size can be 32 to cover the whole images. We know that the kernel better to be odd, so maybe it's better to remove one row from one row and one column from the images. But that's okay. The torch can handle that. Maybe the performance is a little worse, or maybe the result is not that good, but that's okay for now for this implementation. So as I said, we need the input channel and output channel. And what we are doing here is when we, for example, we have 3 channels of image, R and G and B, and we say the input channel is 3, and we want to have like output channel of 3. And DAU unit is, suppose it is like 5. Okay, so it means that we are assigning some centers. We have these centers, and these centers. We have 5 centers, and each of them is a Gaussian function. For creating this one, we create one of them in one channel, and finally we sum and create a complete DAU unit. So I will explain that in a bit. So we have parameter W. So in the paper, oh, this is something, yeah, the paper is a little change after maybe they have implemented something in 6th February. I didn't see that. The paper, the first version of the paper I saw was the one I've seen in the 2018, but hopefully the formulation is same. Yeah, there are more explanation here. That's good. So the main original implementation is this one. So we have a W multiplied by the Gaussian function, and this translation is just means finding the centers of the Gaussian, and that Gaussian is convolved with the input. And let's see about the sigma and other parameters. I hope it's not changed. Yeah, so they showed here that by setting it to the standard deviation 0.5, they can get a very good accuracy. And also it can be learned. So if we learn it, we can get a better accuracy, but we are okay with this. On CFAR 10, on top 1 accuracy, they can get about 57%. We can set the sigma as a parameter, like here, when we define a parameter. So we have mu1 and mu2 as parameter and W as parameter. And we could set sigma as parameter, but just for simplicity and make the system to works better, we just set it to 0.5. So this part of the code is just creating a kernel. If you search for some code creating a Gaussian in 2-dimensional, you can search like creating 2-dimensional RBF kernel mesh grid. You can see that we can use mesh grid for creating, yeah, similar to this. So we are using the mesh grid. We have X and Y axis, and we creating that Gaussian kernel like here. So let's back to the code. So we have that mesh grid, and we set the type to float 32, and we also create a reset parameter. So these parameters on W, mu1, and mu2 can be set by Javier initialization or any other uniform distribution. I just picked this one because in another video we were talking about, I think it was graph neural network. We found this is very helpful for initialization, and that's why we copy that from there. And for forward function, so what we are going to do is, as I said, we are creating, for example, 5 different DAU units based on this example, or based on the code, we are creating 3 different DAU units. For each DAU unit, we are creating a kernel based on that formulation, and we appending them together. And after concatenating them, so we have like 3 different matrices. And we sum these 3 different matrices to create this general DAU unit. And we reshape it. As I said, we have in kernel size by kernel size, and we repeat it. We have 3 of them because each of them is convolved to the image and multiplied by the W. And W is based on the size of the output channel, the max kernel size by max kernel size. So maybe, I'm not sure, maybe this part of the code that we are repeating can be done more efficiently. Like when we say 3 different units, maybe it's good to have, instead of creating based on the number of DAU unit, we have to create them more, maybe in other parameters, DAU unit, number of kernel in each DAU unit. So we can have different strategy here, but one of the things just how the CAM works is just repeating them, and because they are multiplied by the W here, we are not creating redundancy. So we convolve them and we set the padding to the same, and this convolution is coming from the functional torch, so we can pass a kernel, and that's it. And after that, this part of the code is just copied from the, if you search CFAR10 convnet torch, you will have the main PyTorch documentation. You will see that they have loaded the data for CFAR10 for 10 classes. So if you see, this part is same. And then we have our network. Their network is just convolution, doing the max pooling, the linear layer. But what we are going to do here is not using any max pooling, and we are just defining 2 DAU. Number of parameters is about 120,000. In the paper, they mentioned the smallest model they use is like about 400,000. That's why maybe we will not get the similar accuracy that paper got, but the concept is same. So we can add more DAU unit if you like, or change the layer, but we do not use any max pooling because we think that the max pooling is decreasing the resolution. And the reason that we apply the DAU is just keeping the resolution. And also see the number of parameters that we are working on for each DAU unit is small. It's just the mu1, mu2, and w. We are not training any convolutional kernels here. The kernels is just the mu, and after that, just a w, which is element-wise multiplication. So after that, we have this part of the code which define the criterion, which is cross entropy loss, and I use the optim SGD because the paper also mentioned that they use SGD. Yeah, so they said the learning rate is set to very small. This was different in the first paper they mentioned, and I used the parameters that they mentioned in the first paper, and also you can see that I thought that maybe learning rate for mu1 and mu2 for each layer maybe can be a little larger than the learning rate for the weights of the linear layers. So you can use this code if you have any other parameters to change the learning rate specifically. And finally, we have the main for loop. This is also got from the main for loop for training of the torch documentation. And you can see that we are getting from 2.148 to 1.98 so far. This is just 15 iteration. In ConvNet, they are getting from 2.1 to 1.2. We need to reach that. If we reach that, we will get the accuracy like 54%. And as I showed you in the paper, they are showing like 57%, which is a little better than what we have currently in the documentation here. So currently we have not reached that point yet, but I hope we can, because you can see that this is decreasing, but the maybe learning rate is not okay. I tried it. If I set the learning rate too high, we cannot train it very well. So maybe it needs more time, or maybe number of DAU unit I have created is not enough. Or as I said, maybe this part of the code that I have a little the other order that I repeat that. So, but with this loss, I tried to check, and we are getting about 30% accuracy. It was just based on the 20 epoch. So I just set it to 100 and let it run to maybe find the better accuracy. But yeah, that's it. And hope you enjoyed it and you found it helpful. You can use it for one-dimensional signal if you want. And as I said, it can keep the resolution and have less parameters than the convolutional neural network. Thank you and have a good day.